sum is actually following the complementary value of A or the A bar. Whatever the value of A is, that gets complemented and we get the sum part. Then what about the third case when B and C are having 1 0, a value of 1 0? For 1 0, again there are two cases. One is 1 0, another the lower part is 1 0. This is the case where 1 0. And again we'll try to find out the relation. You can see that if A is 0, sum is 1. That means there is a complementary operation again. So A bar equals to S. And for lower part again, if A is 1, then sum becomes 0. Then again a complementary operation that is going on. That means A bar equals to S. Okay, so in that case, when B and C equals to 1 0, the D2 can be replaced. The D2 I can replace it with again with A bar. And the last case is 1 1 when B and C becomes 1 1. That means D4 or rather D3 will be coming at the output. And in that case, you will find that when B and C is 1 1, if A is 0, sum is also 0. So direct relation, when A is 1, sum is also 1, the direct relation. So we can write down at this moment is A equals to S, and this is also A equals to S. So these two are satisfied, and we can replace the D3 by means of A. So now, as you can see, our multiplexer, it is having 6 number of inputs including the select lines and the input lines, but now it already follows all the possible combinations of the inputs with its proper sum output. This multiplexer, this full multiplexer will now behave like a full adder sum part. This will behave like a full adder sum part. So let us try to generate let us try to generate the multiplexer that will be used for generation of the full adder's sum part. So it will have a two select lines, four input lines. So it will be A bar, A bar, and A with the select lines as BC, and this becomes the sum part. And the same way we can also find out the carry part itself. The same way we can also find out the carry part. Which way? Again go for 0 0 approach, 0 0 approach, and try to find out the relation between carry and the sum itself. So you can find out that here the carry and the sum, like you say, you can see here that the carry is 0, the sum is also 0. So obviously A means C, and the lower case here when it is 0 and 0, when sum is A, or rather when okay, for this part, let's not complicate by using an inverting manner, but rather go for the normal way of operation. So instead of, okay, I cannot just remove this. Okay, instead of writing that, let me just erase. So instead of writing directly from the truth table, because it becomes much more complicated for carry part itself, so we will use the truth table or the table of the multiplexer that we had drawn in the last day. So we'll take all the values of B and C. So this is 0 0 0 1 1 0 and 1 1, because we know this is a B and C. So this is D0 associated with it. This is D1, this is D2, and this is D3, and the two values of A are A bar and A. Okay, so this is the table of the multiplexer, and obviously these are B bar, B and C. This is all of the values of B and C, four possible values. So here what we will do, we will go to the truth table itself. What we will find is 0 0 0 1, that's the four terms, and then 0 1 1 1. So here we will write 0 0 0 and 1, then 0, 1, 1 and 1. This is generation of the carry part itself. So this is for generating the carry part, and the final value of the B and C and the A will be coming like the way here you can see both of them are 0. So this comes out as 0. Then for the second term, the lower part, rather this will not be bar but rather only A. This 0 1, one part goes down to A, so this will be A, and then again this is 0 1, so obviously this one will be A, and for the last case upper part and the lower part both are 1, that implementing it's an 1. So for carry part, uh, only the A, B, C will not be there, but there will be association of direct inputs. Direct input means some of the pins must be provided with direct input, because the logic is not very simple like the way we have seen in the sum part itself. Okay, so the carry part will because it's not maintaining the like the way we did in the sum part, it's not maintaining the same simple relation, but rather it's following a rather complicated scenario. So we can directly implement that from the multiplexer truth table to implement any other logic circuit, and we can find out the carry itself. So this becomes our carry out. These two are the sum part. I mean, these two are the select lines. BC I'll be using again in the same way. The first input will be directly given as a value of 0. So no matter what happens, when B and C are 0, this 0 will directly coming. There is no provision of getting carry generated when B and C is 0. And obviously that's true. When B and C are 0, A can have two values, either 0, 0, 0, that does not generate any carry, when 1 0 0, that does not also generate any carry. So in both the cases, the output of the carry will be directly 0. So that's why we cannot equate any value of A with the carry part when considering these two scenarios when B and C are 0. So we directly implement 0, so that when B and C is 0, this 0 directly goes to the carry out itself, right? Because here you cannot just implement them using a normal logic. You have to directly provide 0 or directly connect the input to the ground itself. But for the second part, I can provide that value is A. For the third part, I can provide that value as A, because our truth table is saying so, because our multiplexer table is saying so. And for the fourth value again, as you can see, for the fourth value, BC becomes 1, and for B and C 1 and 1, A can have two possible values, either 0 1 1, that produces a carry 1, or either 1 1 1, that also produces a carry of 1. So for both the cases you can see there is no proper logic behind the relation of A and carry itself. You can see it is converting from 0 to 1, and it's directly moving from 1 to 1. So though there is no conversion, but one thing that is very strict is that the output always becomes 1 whenever B and C values are 1. Irrespective of the values of A, whether it's 0 or 1, that does not matter. When B and C are 1 and 1, we get to see a carry getting generated. That's why the fourth value will be directly providing a value of 1 to the fourth input of the multiplexer to implement the fourth term and the eighth term in our truth table. So the truth table here you can see this eighth term and the fourth term. To implement these two, I need to have a equation to be made like this, so that one must be provided, because it's not following a normal logical equation or a normal logical for relation between A and the carry itself. Okay, so this way this 4:1 multiplexer becomes the carry out part of the full adder, and the previous diagram that we had drawn, this one, there is A bar, A bar, and A becomes the sum part of the truth table. So we require two 4:1 multiplexer to represent. Now you'll be asking, sir, for representation of a full adder, only one single full adder is required all the time. So why use those two multiplexers? What is the requirement of those two multiplexers for creating all those calculations and placing them so that it behaves like a multiplexer, adder, a multiplexer? We don't need to do that because half a full adder is already there. We know the relay circuits of a full adder. Sometimes you will find there are different types of chips which are called as the FPGAs. What is an FPGA? An FPGA is a pre-formatted, is a pre-defined IC or integrated circuit where a millions of transistors are there, millions of small circuit components are there, but it is not dedicated directly by the manufacturer. It is directly not manufactured for serving a proper purpose. The FPGAs, the full name of the IC is the Field Programmable Gate Array. Those ICs many times, the like the Raspberry Pi, like the uh, other Arduino board you use, those ICs that you get to see, they basically comprises of multiplexers. As you can program them to behave like any circuit if you want to. So someone is creating an automatic hand sanitizer machine using a Arduino chip, someone is creating a robot car, or someone is creating a robotic arm using the same chip by changing the program to behave like different applications. To do those types of things, those ICs need to be reconfigured. Those ICs need to be programmed in software as well as in its hardware basis. So we do those programmings by incorporating millions of multiplexer within the device itself. Instead of using a dedicated full adder, what we do, we instead of dedicatedly placing a full adder, manufacturers provide two multiplexers there so that those multiplexers can be programmed to behave like a full adder when required. Those multiplexers can be used to make behave like a decoder. Those multiplexers can be used to behave like a comparator. So the manufacturers provides millions of multiplexers which are programmable. That means you can decide or you can set the inputs and you can set the select lines of those multiplexers by means of programming, and then you can have a what I can say. Then you can have any type of circuit if you want to make by using cleverly redesigning the multiplexer or reprogramming the multiplexer to behave like any circuit you want. So in the fields where some programmable IC is required, the multiplexers plays huge role, most vital role. You cannot just build your own hand sanitizer IC chip that will be dedicatedly doing your work, your program that you have made for your project, right? So it's not possible. It will cost huge amount of rupees to dedicatedly manufacture a IC that you are trying to design or a application that you are trying to design. That's why those programmable ICs you bring and you try to reprogram themselves. And for reprogramming of those hardware components, they are basically uh, used for behaving like different multiple different circuits. Okay, so that's all for today. I hope you have understood the functionalities of a multiplexer that can be used as, let me just paste the attendance link in the chat box.